So here's another conservation of energy situation that we should take a look at, and it is the pendulum. The magic of the pendulum. A lot of people say pendulum with a J or G sound in it. There's no J or G in here. I don't care if you say it that way, but I'm trying in my life to say it as pendulum because that, I don't know. Does that make me artsy? I don't know. But here's the deal with the pendulum. It is a support at the top. So imagine a roof rafter, and we hang a string with a heavy weight on the end. The string has length L, and the weight has mass M. Now, if you pull this thing to the side, because the string is a fixed length, it will have to rise up a little bit. So this pendulum bob and this pendulum bob are different by a height h. And that means that when this thing is pulled to the side, it acquires potential energy. When you let go, it returns to its normal position, and then it undergoes what they call simple harmonic motion. It goes back and forth between potential energy, kinetic energy, and then on the other side, potential energy. And we've pulled this thing aside an angle theta, and it's gone up a distance h. So I want to show you the secret of the pendulum, how you can figure out how fast it's going based on how far you pulled it to the side. And it's really pretty simple. In the world of conservation of energy, we would simply say that the potential energy, when it's pulled to the side, is going to equal the kinetic energy at the bottom. So m times g times h would equal 1/2 m v squared. Well, we did this in the last video. The m's cancel. And you can multiply both sides by 2 to get 2gh equals v squared. So it looks like v is going to be the square root of 2gh, just like it was for the roller coaster. That's kind of interesting. But we don't really know what h is. We do know what theta is. So we have to figure out what the relationship between h and theta is. And that's the secret of the pendulum. So let's make another drawing of this thing. The pendulum is here, and then when you pull it to the side, it's over here. This is an angle theta, and this length is L. But the question is, what is this length right here? L goes all the way from the top to the bottom. L is also over here. And so it looks like we have a right triangle here where the hypotenuse is the L over here. We have an angle theta, and we're looking for a cosine of something. Well, that's hard to figure out, but we did say that this distance right here was h. So this question mark distance is equal to L minus h. That means that in the triangle, we have a triangle whose side is L minus h, whose hypotenuse is L, and whose angle is theta. So, it looks like cosine is the thing to use because this is the adjacent side. So cosine of theta equals the adjacent side, L minus h, divided by L. Now we're trying to solve for h here. And so I guess what we're going to have to do is we're going to have to multiply L on both sides. L cos theta equals L minus h. Ooh, this is looking good. See, we want h to be positive, and it's negative over here. So let's add h to both sides, and let's also subtract L cosine theta from both sides. That's the equivalent of h moving to this side and L cosine theta moving to that side. And then just to be pretty, let's go ahead and factor out the L. H equals L times the quantity 1 minus cosine of theta. And that's the secret to the pendulum. What you need to do is you need to put that in for h. And what we'll wind up with is the official formula for the velocity of a pendulum at the bottom of square root of 2 times g times L times the quantity 1 minus cosine of theta. And that's the pendulum formula, kind of, in a way, at least in the chapter on energy. Later, when we deal with this in terms of time, we'll have a different pendulum. We'll talk about this as a simple harmonic motion oscillator. But you can see that this is why pendulums are sometimes used as wrecking balls to destroy structures, is that you can swing the pendulum back, and then when it swings to its resting position, it will be going at a velocity that you can predict. And the longer the string, the faster it'll be going, and And of course, the more theta, the faster it'll be going. So, all right, let's call that right there.